All right. Let's recap briefly where we left off last time. So we were talking about regression, and we imagined that we had a few points that we wanted to fit. I think they look something like this. And one of the things we talked about is what is this error function, what's the right error function to use? And so we yesterday solved this problem for the case where the error function is measured vertically. So given some model y equals mx plus b, our error was mx plus b minus y. Right? And we went through this problem of setting this up as a large linear algebra over-constrained system. And so we ended up with like an ax equals b, if you recall, by putting all the constants in A, making x be the vector of our parameters, which are the things that we're solving for. M and B, right? And B was basically ended up being the y coordinates. Was A tall and fat, tall and skinny, or short and fat? Yeah, tall and skinny. And so it's over-constrained, and so our answer was found by constructing the normal equations, right? By basically using the AT, the transpose of A, as a way of projecting this entire equation here into the coordinate space that is spanned by the columns of A. Right? And basically what that meant was that we were searching for a solution x which would get us as close as we possibly could get to B. And the error that we had left over would be perpendicular to any direction that we could actually travel. Does that ring a bell? All right. So what we didn't answer last time is what would we do if we wanted to use this error function? And can someone remind me why we might want to use this error function as opposed to the straight up and down? Yeah. Right. So this was the example that I used before where we might want to use the straight up and down version if there was no noise in our x coordinates. Right? For example, if I was fitting the linear trend to temperature on Monday, Tuesday, Wednesday, Thursday. In that case, I know that the x-axis was Monday, Tuesday, Wednesday, Thursday. In a case where I might have noise is something like where I'm measuring a position of a robot. Right? How is the car driving through space? In that case, the x and y positions are both subject to noise. And what we might want to do instead is make the line track as close to those points as possible. So in that case, we would want to minimize the perpendicular distance. Make sense? So I'm going to start off with how we solve this problem with a happy little factoid. The factoid is that whatever line ends up being the right solution, that line goes through the centroid of the points that we're trying to fit. So I'm going to omit the proof for that, but I can post it online if you're interested. It's just a little grungy. But the basic idea is that, again, the line that's going to be our best fit is going to go through the centroid of these points, wherever that happens to be. All right? Now, even if you don't believe that, clearly we can agree that there is some point that this line goes through, right? Such that the, what do I want to say? No, we're gonna say that it's the centroid. Otherwise, my next sentence isn't going to work. All right, so the best fit line goes through the centroid. Now, what does that mean? Well, it means that basically we can take these points and shift them without loss of generality so that the line goes through the origin. Right? Just subtract off the centroid from all the points. Right, and that's what I meant to say. So whatever point it is, we can assume that we can shift the point so that the line that we care about goes through the origin. That's what I wanted to say. Right, everybody agrees with that. Right? No matter where the points are, I can shift them so that the best fit line goes through the origin. Right? And then I can figure out which way the line is tilted, and then I can always shift that line back. Right? And having that, constraining it so that the line goes through the origin, as you might imagine, is going to make the next little bit of math that we do a lot simpler, because we're going to have zeros all over the place. Okay, so let's suppose that we've done that. We've shifted these points so that they go so that the best line fit goes through the origin. Now, what do we know about the slant of this line? Keeping in mind that what we want to do is we want to minimize the perpendicular distance between the line and all of the points. Can we write down a system of equations that describes that best fit line? Well, if there was a perfect solution, right? In this case, in general, we can't expect for us to actually have a line that goes, that is, oh man, I was really tired. Let me strike that, right? What we want to do is we want to make sure that all the distance between all of these points is perpendicular to the line. So how might we describe the orientation of the line? We'll want to minimize that, that's right. But how do we characterize the orientation of this line? Or if I use the word hyperplane, how might we characterize where that hyperplane is in space? With the normal vector, right? Right, so let's break out a normal vector. That we could do that. It's actually going to be even easier if we describe the orientation of the line in terms of the unit direction of the line. Oh, did I mention I'm tired today? All right, so we're going to have a vector here. Let's call it u, which is the direction of the line. All right. Now, can someone tell me what the next step is? What relationship do we want to have between all of our points, P1, P2, P3, blah, 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 blah?
They're perpendicular to that vector.
Right. We want the error between this point and the line to be perpendicular to u hat. Right? How do we express that?
The vector minus the prediction of the whole loop.
Right, so how do we do that? So what I want to know is, I want to know what point on the line is this point right here, right? So let's take P2 because I got too many symbols over here by P3. What I want to know is what's this point, right? What is that point? And I think you just said it.
Prediction of the vector P2, the point on that line.
Right. So it would basically be P2 dot u, right? That's going to measure how far to go. And then we go that far along the u direction, right? So P2 transpose u, right? This is the length because this is the dot product, right? That's basically projecting this vector onto the u hat direction. But of course, that's just giving a distance to travel. The last thing we need to do is actually move in the direction u hat that far. All right, so this is a scalar, and this is a vector. All right. Now, what property do we want to have happen here?
P minus this is perpendicular to u.
Right. At this point, if we now consider P2 minus this, right, that's this vector. This is our error vector, is perpendicular to u. Everybody on board? All right, so how do I express that? Here's my vector, and I want this to be perpendicular to u. Right. What do you guys think? Now I want to do this for every point that I've got. And you guys can probably already see that I'm going to be able to manipulate this into a form where I'm going to have points. Let's see. Should we multiply this out? P2tu minus ut P2 U equals 0. Now I'm realizing that I didn't actually work this example fully out in my notes, and I'm afraid that I'm going to regret it. But maybe we can power through this with the power of 75 people. I lost a U hat here. So what should I do? Say it again? Sum over all I, for sure. Let's see. You know what? I'm going to write this a different way, and I think we're going to agree that it's going to be the same thing, but I think it's going to give us a happier approach. So we do want this to be true, but another way that we could express this constraint is that we want to minimize the sum of the distances. Right, so this is our error vector, e sub I. Well, this is e sub 2. If I change these to i's, all right, so let's do this instead. I think this is going to work better. All right, so if this is my error vector, I might still want to minimize the sum of squared distances. Everybody agree with that? All right, so that would be EIT times EI summed over all I. So now we can multiply this guy out, PI minus PI transpose U, blah, 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 transpose PI minus PIT, U, U, T. All right, oh, no T, no T. Right, and this expression here, so just to recap, since I made a misstep, this is the miracle of being in front of the IQ depression zone, that your ability to solve math problems goes down very rapidly the closer I get to the whiteboard. All right, so this, just to recap, this is our distance. Let me say it this way. Here is point PI. This is the point that we constructed here, the point on the line closest to P sub I. Right, so their difference is the error vector between my point and the point on the line closest to it. Everybody tracking? And so this is the magnitude of that vector. How long is it? Right, it's very similar to what we did before. All right, now we can multiply this sucker out. All right, and we're going to get PIT, PI, that's this term, and now minus PIT, PIT, U, minus PIT, uh-oh, I'm doing that backwards. There's a transpose in there. So I need to go U transpose PI times PI. Am I still doing this right? You guys can see the whole picture better than I can. And now I'm doing the last term on each side, which is U transpose PI, PIT, U. Do we like that? All right. Can we do any simplifications that are worthwhile? Sure. Right. What's the simplification that we can do? Say it again. U hat is? Well, the magnitude of U hat is 1, but the vector itself isn't 1. Do we have any expressions in here where we're computing the magnitude of U? I don't see one.
I think the last three terms are equal in magnitude.
Well, I'm not sure about this guy, but this term and this term certainly have something interesting going on with each other. Right? So what is this guy in terms of a type of linear algebra thing? Is it a matrix, a vector, a scalar? A scalar. What's this guy? A scalar, right? They all have to be scalars. And this guy is the transpose of this guy. right? Didn't we saw this happen last time, right? Not too surprising. So I can combine these guys, and let's see. Two PIT, PIT, U, U. And now I've still got this guy, U, U, PI, PIT, U, U. Okay. Let's see, where are we going with this? Oh boy. This was so much easier in my notes. I did it in PowerPoint, and it was like, there we are. All right, so this is the error function. What do we want to do? We want to minimize the error. Right, we're in uncharted territory. We're going to solve this together, one way or another. What is the thing that we're minimizing? We're minimizing this expression. What's the thing that we have control over? The u. Right, so what we want to do here is differentiate with respect to u. Okay? So how do we do that? Let's see. There's a simplification in here that I'm just zoning on. One of these terms is supposed to drop out. So this guy would go away, right? And this, what should happen here is we should end up with basically this guy. This guy I think is supposed to end up going away as well, and we should end up with this guy and just this guy left. And so we should end up with this guy equals 0. This guy is a scalar. Right, these are all scalars.
So if you simplify the third term, it should come out to be equal to the other two terms. So one of them we can.
The third term we can drop the first u transpose and start u.
I believe that, because that gets me closer to where I want to be. Why is that?
Because u transpose p is a scalar, the second and third, u transpose p is a scalar, and p transpose u is again a scalar. So both of them will come out. Then u transpose u is just 1.
I like it. That's very clever. Did you guys see that? Right, so u transpose p, this is a dot product. This is also a dot product, which means that this is going to be a scalar and this is going to be a scalar, which means we can pull out the product of those scalars out here, and we're just going to be left with UTU, and we said that u was a unit vector, so UTU is just 1. So what we should end up with is just the square of this dot product. Good, I see a couple questions.
So in the error term, in the beginning, the PI transpose dot product means no big problem. Yeah, the PI transpose dot product you have is already scaled. So you're mixing multiplication and dot product, so that's why all the confusion comes.
Well, so this is a sensible expression in terms of linear algebra, but you're right in that some of the sub-expressions are scalars. Right.
So that's already a constant,
Right, and I suppose if I had written this out as like lambda or something,
right?
then I probably wouldn't have gotten so tongue-tied over here.
You're treating that like a dot product
Right, well, I'm expanding it out, which is certainly making my life harder. I think you're right about that. So let's see, does this get us where we want to be? So this was going to be just u, UTPI, and that's a scalar, and it's going to be this squared, right? And this guy is going to be the same thing because this is a dot product, which is going to give me a scalar. And this is going to be a dot product then, which gives me a scalar. Good. See, I'm glad we did this. All right, and hopefully we're going to end up with the right answer here at the end of the day. So we're going to have this quantity here, which is also UTPI. Right? I'm just writing it in the other direction so it matches this dot product for clarity. And we're going to end up with that squared. And we have minus 2 here, I p sub I t p I. OK. And of course, I can combine these terms. So I've got minus 2 of them here and plus 1 of them here. So let's just make it minus 1 of them over here. All right. Whew. I'm feeling a lot better. Thank you. All right. So are we ready to go now? So we should differentiate, right? What's that going to look like? So this is now our cost function. Well, it's still our cost function. The sum of all EI transpose EI is this. I'm now going to differentiate with respect to u. This guy is going to go away because this doesn't depend on u. Right? And remember, u is the thing that we're solving for. U is the direction of the line that we don't know. Right? So this guy is going to go away, and we're going to be left with this guy, which is going to be 2 pi tu equals 0, summed over all I. I switched the transpose around again. Everybody okay with that? And the 2 goes away. And now I'm feeling happy. Right, this is actually exactly what's in my notes. So thank you for helping me get unstuck. Appreciate it. Yes?
But this is not the same as the constraint of the problem, because the points, the e's have to be perpendicular to the u. But I was hoping that you said they're equal things. I was hoping that once you get derivative, you would get to the same expression as the constraint of the problem.
What do you...
The problem was that the error terms dot u was equal to 0. So to make sure that these were perpendicular.
right, so...
I don't see the connection between that constraint and minimizing the errors.
Well, so we know by the way that we formulated the problem that we've minimized the cost function, right? And so if there was some way of moving u, then this would have moved u so that they were perpendicular. I agree. Let's see. PITU. Let me think here for a second. Let's draw a picture of this. So again, we're assuming that the optimal line goes through. So it goes through 0. Here's our PI. So PI. Now I'm exploring this question. It's Ibrahim? Amir, sorry. So what this equation is telling us here is that what we want is for the dot product of each vector from 0 to the point times u to be 0. And you're right in that's right. So the fact that this point here that we didn't, it's as though we didn't compute this point and that we used this point instead. Now I think that's going to work out okay for the fact that we translated all the points so that their centroid is at 0. And so whatever dot product we had from this guy, because this guy does have some projection onto u, is being canceled out by the dot product of some other p sub i's, because we've translated all the p sub i's to the origin. That's a good question. and it's a little hard to see why that would be. But given, is everybody tracking my explanation here? So it was Amir had a great question, just to recap. Why is it that we ended up with this dot product constraint, which is just saying that the dot product of the vector from 0 to the points themselves and the u vector is 0? When what we started off by saying was that the dot product needs to be 0 from this point to the point on the line closest to it. Right, so compare this expression, the expression that I started off trying to solve that I got stuck on, right, because that was hard to manipulate. That was basically, we were saying this guy, e sub I dot u, should be 0. And we agree that that should be true, but the tension is that what we ended up with was just this equals 0. All right, and so the reason that's happening is because we've assumed that we've translated all of the points so that their centroid is at 0. So it is, in fact, the case that pi, the dot product of pi and u, is non-zero. But this constraint here is just saying that the sum over all the points needs to be 0. And because we've shifted all of the p sub i's so that their centroid is in the middle, the fact that we end up with a positive dot product here is going to be offset by other points that had a negative dot product. Who's on board? All right, great. And who's completely embarrassed for me that I struggled through this problem so much? Just me? Oh, and Rob. Thank you, Rob. You're so nice. Okay, yes? Right, this is the derivative. So the way that we solved this problem was that we wrote down the cost function, which was a squared cost function. We expanded it out. We took the derivative with respect to u, did some simplifications with some help from people back there, and then it reduces to this.
So you are now explaining what the limit is?
Say it again?
Are you now explaining what the geometric meaning of this equation?
Well, so we have this intuition that it has something to do with the dot products. The average dot product of all the points and the u vector needs to be 0. Right? All right, so now let's actually consider solving this. Actually, in 2D, at this point, we could probably go home and just compute the average orientation of all the points and call it a day. But let's be a little more systematic about it. So what we're basically going to have here is we're going to pick a u so that the mean is 0. So the way we can write this is we can take all of our points, P2, P3, this is P1 transpose, P2 transpose, Pn transpose. And we're saying that if I take my u vector here, and so this guy is going to be the first term, this guy is going to be the second term, and so on and so on and so on, that on average these should all be equal to 0. Right, so now we're going to be a little bit gross and just basically say, well, if we tried to make them all 0, that's going to be equivalent to trying to make their average 0. Right, because it's a squared error term. If I'm off by some amount here, I'll have some corresponding error here. So what we have now is an ax equals b problem where b is the 0 vector. So can someone solve this problem in their head for me? X equals 0, right? Which is not a very good unit vector. Right, and this is a problem that comes up. Actually, Michael had asked about this problem a little while on the first lecture about null spaces. The problem that we ended up with here is that if I have an ax equals b problem and b is 0, I have this significant problem that there's a trivial solution. I can just stick x equals 0 in there, and it's going to be true trivially. What I really want to know is what's the smallest I can make this for some x with bounded magnitude. And solving this problem is going to be what we're going to do next. So let's table this for just a moment and consider an interesting matrix. This interesting matrix is going to tell us how to solve this problem. Do I want to go down this road here? Let me just make a little mental checkpoint. I'm trying to decide if I want to step into another abyss of a problem I didn't work out in detail. No, I don't. All right. Maybe I'll put it in the notes online. I was going to do a slightly more careful derivation for one of the steps I glossed over there. I'll put it in the notes online. I'm tired of feeling stupid up here. Okay, so let's consider a matrix. This matrix can be factored. I do need to point out one thing. This matrix is tall and skinny. Right, so to actually solve this problem, we'd really want to be looking at something like an ATA x equals ATB, right? But still, that trivial solution is still there. So the next thing I'm going to be talking about has to do with square matrices. So we're really going to want to talk about ATA here. All right, so let's suppose we have some matrix. It's a square matrix. And let's suppose that we factorize it in a particular way. So this factorization is going to have a bunch of interesting properties. The first one is that this middle matrix, so here's some square matrix. It's going to have the middle matrix is going to be diagonal. It's going to be 0 everywhere except along the diagonal. And then these two matrices are going to be orthonormal matrices. So what does that mean? Say it again. You're ahead of me, yes. So we'll get there. It's actually singular value decomposition, but but so this matrix and this matrix here are both going to be orthonormal matrices, which means that the magnitude of each of the columns is going to be 1, and they're all perpendicular to each other. That's an orthonormal matrix. So we're going to call this one U, we're going to call this S, and we're going to call this V. Actually, we're going to call it V transpose because we like to think about the columns of V sometimes. All right. So let's given the properties of orthonormal matrices, let's suppose, one more thing about this factorization is that we can write it out so that the values of S descend in magnitude, so that this is the biggest and this is the smallest. Right, so maybe this is like 6, 3, 1, 1, 0.2, something like that. And then these are orthonormal matrices. Now, if I could pick any x I wanted over here, how do I get the longest vector over here? And let's make this an x hat, right? You give me any unit vector you want, and I want the longest vector I can get over here. Which vector do I pick? And I don't care what direction it's facing in. I just want to maximize the length of that vector. Right. So whatever vector is in the top row of V is going to maximize this expression. Why is that? Well, so here's the basic idea. This is an orthonormal matrix. Right? All its eigenvalues are 1. It doesn't do anything about changing the length of my vector. Neither does this guy. It's also an orthonormal matrix. All of its eigenvalues are 1. The only thing that changes the length of my vector are these diagonals. Right? And so my vector over here is going to start picking up certain elements of these guys. And what I want to do is I want to have the maximum value here. Right? So another way of saying that is pretend this wasn't here. What vector would I want to put on the right side that maximizes the value on the left side? 1, 0, 0, 0, 0, 0, 0. Right? Given that I've got unit 1, a length of 1 to spend, and I can put it in any direction, what I want to do is I want to put it in the direction that's going to get the most factor of 6 picked up. Everybody with me? Thumbs, just so Great. So now, given the fact that we introduced one more rotation matrix, one more orthonormal matrix, what I want to do is I want to pick a value of x such that VTX is equal to 1, 0, 0, 0, 0. And the matrix the vector that's going to do that is the top row of this guy. Right? Another way of seeing that is that this guy is orthonormal. All of its columns are perpendicular to each other. If I pick this guy, I'm taking the dot product of this vector with itself, which is going to give me magnitude 1. And because all of these rows are perpendicular to each other, the dot product of this guy with any of the other rows is going to be 0. All right, everybody happy with that? Great. Now, if I wanted to minimize the value of this, what x would I pick? Right, the bottom column of, the bottom row of V transpose. Okay. So, if it turned out that our ATA matrix from just a moment ago, here's our ATA matrix, if we could write it in the form USV transpose, how would we want to pick our U? How would we want to pick the direction of our line? Right? We want these things to be as close to 0 as possible, right? So we want the product ATAX to be as short in length as we can possibly manage. Right. Right. So if we could take ATA and we could factor it into the form USV transpose, then we would want to pick this row of V transpose to be the orientation of our line. Right? Because constrained that this guy has to have unit magnitude, that's going to pick up the smallest eigenvalue of S. And this is going to give us the shortest line over here. The line with the shortest length. Everybody on board? All right, so that is actually how we solve this problem. This is the singular value decomposition, which exists for any matrix. Doesn't matter whether A is square or tall or whatever. This exists for every matrix. All right, so let's do a little brain teaser, and then we'll build some more intuition about singular value decomposition. So I just said that this matrix, USV transpose, exists for every matrix. Right? If I've got a, let's go back to a square matrix A. It also exists for A inverse. So how do I compute the singular value decomposition of A inverse if I already know the singular value decomposition for A? So USV transpose. And A inverse equals what? Right. So there's a couple properties you've exploited. Right, the first one is, of course, what is the inverse of an orthonormal matrix? It's transpose. Right? That makes sense because all the rows are perpendicular to each other. All you have to do to get the identity matrix is make sure that along the diagonal, you're computing the dot product of a vector with itself. Right? Any other positions where I doesn't equal j, you're going to end up with 0 because all the rows and columns are perpendicular to each other. All right, so we can basically apply this rule here, USV transpose inverse, right? And we can push this inside. How does this work? Well, it's going to be V transpose inverse, S inverse, U inverse, right? This hasn't really done anything interesting yet, but now exploiting the property, I'm sorry, I've forgotten your name? Nira? Exploiting this property, since V is an orthonormal matrix, V transpose inverse is V. And U inverse is U transpose. What is S inverse? Right. The happy thing is that S is a diagonal matrix. Right? So its inverse is just going to be exactly another diagonal matrix, except with 1/6, 1/3, 1, 1, and 2. Everybody on board? So this is just going to be S inverse, which is easy to compute. Great. So if the smallest singular value of A was 0.1, what's going to be what do we know about A inverse? Right, 10 is the largest one. Okay. Now let's just briefly consider the case where A is not square, just so we can get some dimensions taken care of. So let's suppose I've got A. I'm actually not going to draw it because it gets confusing in this case. Let's suppose A is m by n. So the main thing to remember about a singular value decomposition is that you've got a matrix with an m-dimensional space related to an n-dimensional space. Right? You can view A as a projection from one to the other. And so somehow this matrix here is a marriage, is a mapping between an m-dimensional space and an n-dimensional space. Yep. Now, if you were living in an m-dimensional space, or any dimensional space, one thing that would be really nice to have is an m-dimensional basis, right? M vectors which span the full space. So singular value decomposition is always going to give you that. U is always going to be m by m. It's going to be a set of basis vectors for an m-dimensional space. Similarly, V will always be n by n. Right? It's going to give you an orthonormal basis for an n-dimensional space. Right, so what does S have to be? M by n. Right? So in this case, I guess I drew it sort of square. All right. Now, if this is a bizarrely shaped matrix, this is going to end up, let's suppose A is tall and skinny. Then we're going to end up with an enormous matrix, right? Because that's we need a set of basis vectors that spans the m-dimensional space. And we're going to end up with a tiny little v, right, corresponding to this length. And then our singular vectors are going to be shaped like this. Make sense? All right. Now there's also, if you go to Octave or MATLAB and you type in the singular value decomposition, you might end up with what's called an economy singular value decomposition. So what is an economy singular value decomposition? Well, so what is the rank of A if A is an m by n matrix? In what dimensional space, what subspace do the columns of A span? At the most. So let's get it exactly, let's get a tighter bound yet. So what if m was smaller than n? Right. So let's ask it this way. I've got a 100 by 3-dimensional, an A matrix that's 100 by 3. In what space, what is the dimensionality of the space that I can span given the columns of A? At most 3, right? It could actually be even less if those columns were linear combinations of each other, right? All right, what dimensionality space can I span using the rows of A? Now there are 100 rows of A. Each one has 3 elements in it. 3-dimensional space, right? I can't do more than 3 because I'm only in a 3-dimensional space. Okay? So if I have a matrix that's not square, then I know that the rank of my matrix is going to be less than its largest side, right? If I have a 100 by 3-dimensional matrix, I know that it's going to be rank 3 at most with our little legalese provision. Now, what does that mean about the null space? In other words, the space that I can't reach by taking linear combinations of the columns and rows. Max of m comma n minus min of m comma n. right? So as the matrix gets really tall or really strangely shaped, as it gets less and less square, the null space is getting bigger and bigger. Now, the funny thing about a null space is that it's a place you can't get to, right? Why do you need an orthonormal basis to span a subspace that you can't get to anyway? You guys see what I mean? Okay. So let's suppose that I've got my 100 by 3-dimensional vector. It'd be really useful for it to have an orthonormal basis that describes all the places I can get, right? Because that's useful, that I can use that to help compute solutions to ATA, least squares problems. The null space is all the places I can't get, right? There are applications, in fact, the one that we're solving here is one case where we do actually care about the null space. But in a lot of cases, we don't actually care about an orthonormal basis for the null space. Right? If I was solving an AX equals B problem where B isn't 0, an orthonormal basis for the null space isn't useful to me. Right? All I want to do is I want to get to B using an orthonormal basis for the places I can get. Does that make sense? The null space, right? In fact, the null space isn't even uniquely determined. Right? So let's suppose I had a 4 by 2 matrix. I don't like that. Let's a 5 by 3 matrix. And let's suppose that it's rank 3. So my null space is of dimension 2. How many different orthonormal bases are there for that null space? Infinite, right? It's a 2-dimensional subspace. This is good, so is this, so is this, so is this. Right? There's nothing special about that orthonormal decomposition for the null space. It's not uniquely determined in any way. I could take that space and rotate it arbitrarily because they all have the same eigenvalue. It doesn't matter, right? They're all interchangeable. So here's what I'm getting at. In many practical cases, we don't care about computing an orthonormal decomposition for the null space. We don't need a set of basis vectors. But if you're actually implementing the linear algebra, it takes a lot of time to compute them. So that's where an economy SVD comes into play. An economy SVD is an SVD where we don't bother computing an orthonormal basis for the null space. So what does that look like? Let's try an example with a tall and skinny A. Here's a tall and skinny A. What dimensions should U have? So how tall does U need to be? It still needs to be tall, right? There's no doubt about that. In fact, the multiplication wouldn't even work unless it were tall. But intuitively, it makes sense because we know U is going to be an orthonormal basis for in m-dimensional space. So those vectors had better be of length m. Right? So now the U vector is going to contain an orthonormal basis for everywhere for the subspace that is spanned by A. So how wide is U? Right. So let's call it short. Here's U. Right, everybody see what happened? Right, all of these guys here, these all correspond to the null space. These are the basis vectors that span the null space. Right? And if we don't care about the null space, it's cheaper not to have to compute these. All right. How about the far side over here? What is V going to look like? It's actually going to be the same as we had over here. That's right. How do we reason through this? Well, it's got to have short dimensional vectors like this, right? Because that's the space in which we're listing basis vectors. And then it's going to have, how many is it going to have? Rank of A. It's going to have rank of A of them. And in this case, this determines the rank of the matrix. So we're going to end up with the same size here. And now what goes in the middle? Short by short. And what do we know about all the values in there? It's going to be diagonal, and they're not going to be 0. Right? Another way of viewing this is that right, we could list more vectors. Right? Here are the singular values, right, going along the diagonal. But really, they're all 0 after this. Right? There aren't any more. Right? So there's no information here. Right? This is a diagonal. This has to be a diagonal matrix. This section can't possibly do anything for us. Right? So we're going to crop that off, kill off these columns. Now, if A is fat and skinny, we're going to have something sort of complementary happening. U will be the same, and now V will be smaller. Right? So the way to draw out the sort of block schematic for an economy SVD is to keep in mind that ordinarily the full SVD has these full basis decompositions in the m-dimensional space and n-dimensional space. An economy SVD is going to drop the extra ones that correspond to spanning the null space. How many of you are comfortable with that idea? Right, and so the reason I spent so much time on this is that when I first started doing some hacking, I think actually Rob might have been there. We've got this SVD implementation in our yeah, Rob's rolling his eyes. This SVD implementation in our linear algebra toolbox that computes economy SVDs, which most of the time is perfectly fine until you're trying to solve one of these AX equals 0 problems, because now you need a vector that's in the null space and it doesn't give it to you. And that's very irritating. So in MATLAB or Octave, it's no problem. You can request, always give me the full SVD, the non-economy SVD. In our particular linear algebra toolbox, you can't. It's very annoying. Okay. Great, so this is a little mystifying. I can tell you that the SVD exists for all matrices, but what I want to do next is to build some intuition for what the SVD is really doing. Why does it always exist? In fact, we're going to compute some SVDs by inspection next. So this is something I think is kind of fun. How many of you can compute an SVD for anything in your head? Well, actually, some of you can. You're just not thinking simple enough. What's the SVD of the identity matrix? I times I times I. Yeah. So we're actually going to start with simple examples like that, and then work up harder and harder and harder, building up some intuition about how U, S, and V collude to build us an A matrix. Yes?
My question is, suppose you have AX equal to B, will the economy SVD not work only when it's AX equal to 0 or for all sets of B's where the B doesn't lie in the column space area?
I'm going to need to parse that a little more slowly. So if you are solving AX equals B and B is not 0,
Space of A.
if it's not in the null space, right, then there's
It's not in the column space of A. As in it is in the null space, but it's not 0. It's some other vector.
okay.
Will the economy SVD work then, or will it not? Because again, any combination of my column vectors is not going to give me my B.
I don't know that I've ever seen that situation actually arise. That's interesting.
The solution doesn't exist in the space. It doesn't exist in the column space, exactly. So I can increase the dimension and solve, right? So I mean, in that case, the economy SVD shouldn't work. I mean, the purpose of doing this is assuming B doesn't lie. For example, in the two-dimensional case, all these points do not lie on the line. That's
right. So if B lies in the null space of A, then you still want the full SVD, because you need the orthonormal basis in the null space in order to come up with a solution.
So it's not just for B equal to 0, but for all of these in the null space.
That's true. I've just never seen that problem arise in nature. Usually you end up with a problem where either you're doing like a linear regression problem, AX equals B, and you can actually solve for that because you've constructed the normal equations. Although, actually, you
You will never be able to get B with any combination of X because it's in the null space.
right. So but you might still want an orthonormal decomposition to find the closest one you can. All right, that's a good question. I might have to think about it a little more to see if there's a practical scenario where that would come up. That's interesting. Okay, so let's start off simple. So the way we're going to think about the SVD is as 3 projection matrices. So we've got USV. We're going to stick with square just so our heads don't hurt. And we're going to basically imagine what happens if I take a vector over here and map it over here. Right? So one sort of thought experiment is how can I build up A? Right? Let's suppose this is A over here. So let's suppose I put in x hat direction here. What am I expecting to get over here? Right, right. So it's just like right. So you could mentally imagine pulling these all back together, right, into one matrix, right, and then 1 0 0 0 1 0 0 0 is just picking off the first column of the product USV, and of course the product is A. So if I put the x hat direction over here, what I should end up with is the first column of A. Similarly, if I put in 0 1 0 0 0, what should I get? The second column of A. Right? This should be familiar from, I think, the first linear algebra review session where we looked at projection matrices, and we talked about how a projection matrix can be interpreted. You look at the columns, and that's where the unit vectors ended up. Does that ring a bell? All right, so here's the idea. We're going to consider the various unit vectors in our two-dimensional space. We're going to do two-dimensional problems. And we're going to try to figure out what sequence of operations gives us the corresponding vector in A. So let's start off with a trivial example. Let's let A be the identity matrix. Right? We already know the solution, so this should be a nice no-brainer, right? So we can actually draw these guys, right? We can think about these guys as vectors. Here is the x. This is what happens to x hat direction, which is still x. Right? Let's call this x hat prime. And here's y hat prime. All right, and what we want to do is start over here with our x vectors, right? And find a sequence of 3 transformations that get us from this space into this space. Now the constraints, of course, are that this one and this one are both orthonormal matrices. Right? So what kinds of things can we do with orthonormal matrices? Rotation, reflection, and actually sort of permutation. Right? So if I had, let's suppose I just did this, x and y. Right? Suppose, I mean, in this case, A is this matrix. Everybody see how that corresponds to this figure? Right? So one thing we might ask is, what sequence of transformations could we apply to get from here to here? Well, so what could we do? Well, basically, we want to, there's a couple different solutions. Somewhere along this chain of 3 transformations, we need to switch the x and y axis. Right? We could actually do that here or here in this case, and just set the others that we aren't using to the identity matrix. Right? So the SVD of this guy could be, let's do I, A. Right, this works in this case because A is itself an orthonormal matrix. That's a very simple, happy case. Okay, great. Ready for a slightly more complicated one? All right, let's switch these back around because otherwise I'm going to start making mistakes. And I've learned my lesson about going off script. All right, so this is now back to the ordinary direction, which means that we've got this. And so that's where we were. Let's introduce some rotation. So let's make x prime go here and y go here. How do we achieve that? So what's the difference between this guy and this guy? It's a rotation. Right? It's a rotation by 90 degrees. And so where can we stash that rotation? Where can we put it in this system? In either of these, right? What's going to happen here? Right, this is the one that has to be diagonal. It's going to be the identity matrix, y.
Because we are not changing the length of the vector.
Right, all the vectors are saying the same length. There's no scaling going on. So it's a complete giveaway. If all the vectors are the same length from one side to the other, that the eigenvalues are all 1. Okay, so in this case, we have a rotation by 90 degrees. We need to stash that somewhere. Let's put it here just for giggles. The rotation matrix for 90 degrees is cosine of 90 times the minus sine of 90, sine of 90, cosine of 90. And we can put the I there as well. Make sense? Okay. What's next? We also could have done 45 degrees, right? That would have been fine. Let's do this. Here is x hat prime. Here's y hat prime. Right? And now this guy has a length of 3, and this guy has a length of 1. How do we achieve that? Using our 3-step dance move, right? We've got an orthonormal transformation, a scale transformation, and then another orthonormal transformation. How can we get from here to here with those 3 dance steps? What should we put here? I. Why? We don't need to rotate anything, right? In fact, this is exactly the same orientation as that guy, so let's put an I here as well. Now what do we put for S? 3 and 1. Yep. Very good. Okay, now we're going to get a little more interesting. Is this making sense so far? So here's x and y. Right, so what is the matrix that I've drawn here? Let's call this, let's say this guy has a length of root 2, and this guy has a length of 2 root 2. So what vector do I have here? What is this matrix? What is the A matrix that corresponds to this vector drawing? What have I plotted here? These are the vectors corresponding to the columns of A, right? So the way that the A that this corresponds to are the coordinates of the x vector, which are, thank you, 2, 2, and the y vector, which is minus 1, 1, right? So, eventually, we're kind of cheating right now. We're making this simple, we're kind of focusing on the geometry. But in reality, you can always think about this as I give you some matrix that corresponds to some vectors in space. And now the game is how do you make those vectors from the unit vectors in 3 dance moves? Okay? So how do I do this one? Clearly, there's some scaling and rotating going on. Does it matter which order I do it in? Definitely. Actually, it matters a lot, right? So what would happen if what's the right answer? Do I rotate first and then scale, or do I scale first and then rotate? scale first, right? What would happen if I rotated first? Well, we can actually try that, right? Let's suppose I rotate by 45 degrees. That would give me this, right? And now I'm going to scale 2 units in one direction, 1 unit in the other direction. So what that's going to be is x, it's going to look like this, right? Because I'm scaling 2 units in the x direction and 1 unit in the y direction. Right? Everybody see that? So the order definitely matters. So what we're going to do instead is first rotate. I'm sorry. First scale by 2 root 2 and root 2. Right, and I can fill those in over here, 2 root 2 and root 2. And of course, this is going to be I, because I'm not using this guy just yet. And now I put in my rotation of 45 degrees, right, which is cosine 45 minus sine 45, sine 45, cosine 45. Right, there's your first non-trivial SVD worked out on pencil and paper. Feeling good? That's awesome, right? Okay, let's try another one. This is the origin. Let's make our x vector look like this and our y vector look like this. And just to exaggerate this a little bit more. Right, that is not 90 degrees between them. I'm the world's worst artist, right? My intention is that this is vertically bisected. Maybe my artistry matters a little more than that. How do we get this? Say it again. So let's suppose that we just do a scale, that we just fiddle with these two guys, right? So that I scale and then rotate. What's the angle between two vectors always going to be? 90. Right? So in fact, I'm going to have to do something here before I scale it, because that's how I change the dot product between these two vectors. Right? So basically, what's the game? If I take my two axes, and then rotate them so that they're not axis aligned, and then scale them, I'm pulling and pushing them closer and farther away from each other. Right? And then I've got my final rotation to do this. Right? So what's our game going to be? It's going to be, we're here from your direction. We're going to rotate, scale, rotate. There's a question?
I have a maybe a question, but I have a little disconnect here. SVD was presented as a way to decompose a original matrix of degree.
Right.
But you're doing something totally different here. You're not decomposing it. You're just you're starting with some matrix and you're doing some manipulation to get to another matrix.
So
Why is it this?
why am I doing this?
Is this SVD? Because I thought SVD is a decomposition.
It is. Right.
What is this decomposition?
Right, so the way that a numerical math package is going to compute this is going to look completely different. But it's going to be considered a decomposition. We're taking A, and we're writing it as the product of 3 matrices. Now, the sort of crazy dance I'm doing here is trying to give you some geometric intuition for what's going on. Right? And so we can describe this decomposition as being 3 transformation matrices. Yeah?
So basically, you want to find the simplest, like, how do you start with, like, you want to have like an I term if possible, like an identity matrix in one of the 3, constructor SVD. In a sense, is it unique? Can we find another SVD that corresponds to this that doesn't include I matrix?
Yeah, so that's a fair question. So the sort of construction that I'm doing here does not constitute a proof in any way for this being unique or for such a decomposition actually existing. So, in reality, you're going to be using a package which you give your matrix to, and it's going to factor it. Now, there are in general, given what I've told you so far, the SVD is not unique, right? For example, I could multiply this by -1 and this by -1, and everything would come out the same. But with enough additional sort of constraints, like if we constrain these all to be, I forget exactly what constraints MATLAB uses, but I think MATLAB imposes enough additional semantics to these things that the SVD ends up being unique. Do you remember, Steve?
I'm not sure.
Right. In principle, this factorization isn't unique because you can add in -1s and things like that. For very simple matrices, like imagine when I had I over here, you can imagine there are all kinds of goofy things I could do here. I could put any orthonormal matrix here, I, and the inverse of that orthonormal matrix here. Right, so I think actually even, well, so that's a repeated eigenvalue ambiguity. So
Anytime we have repeated eigenvalues, you can just think of a number of
that's right.
bases, yeah.
Right, so kind of like in the null space where you've got, let's say, a null space of rank 3, there's going to be some three-dimensional space, and any orthonormal basis that spans that space is indistinguishable from any other one. That's actually true whenever you have repeated eigenvalues. So if I had repeated eigenvalues of eigenvalue 4, let's suppose I have two eigenvalues of magnitude 4, there's actually a two-dimensional subspace where that's all indistinguishable, right? And so any orthonormal basis decomposition of that space is arbitrary up to some rotation, right? If I'm a matrix and all of my eigenvalues are 2, right? I'm describing some two-dimensional space. Doesn't matter what orthonormal basis I pick, right? They're all equally good. There's no way to distinguish between them. So to answer your question, SVD cannot be unique, right, for the reasons we've talked about, but we can nail down a lot of the ambiguity by constraining things in places. Yes.
Is there a selective meaning for eigenvalues?
Yes, there is. So we're going to talk about that in I think 2 more slides. So hold that question. All right, so back to our question, our problem here. We want to construct these vectors out of our unit axis vectors by doing some rotation, some scale, and some rotation. And I think I already danced the maneuver for us. Let's just write it out so it kind of makes a little more sense. So what's the first thing I'm going to want to do? Right, so rotate it 45 degrees. Or I could actually rotate it minus 45 degrees. Doesn't matter a whole lot, right? Basically, the key here is that because these both have the same length, I need to arrange it so that when I do the scale, I can use one of my eigenvalues to scale these guys. And that's going to squeeze them closer or farther apart. Right, if these were slightly different lengths, what would I do? Suppose this guy had length 3 and this guy had length 4. So I'd want to rotate it some different amount so that when I multiply in the y direction by some amount, they end up being, one of these ends up getting amplified more than the other. Right? So I'd want this one to point farther down than this guy. Does that make sense? How many saw what I meant? Okay, great. All right, so here we are. We're going to rotate by 45 degrees. Then we're going to scale by some amount. And the amount of the scaling in this case really depends on what angle I need to achieve here. The closer these guys point together, what am I going to do to the scale factor? At least it's going to be bigger in the ratio between the scale factor in the y direction and the x direction. As that gets bigger, these guys get closer and closer together. So in this case, I don't know what that is. 6-ish. 6-ish, right? 6-ish in what direction? In the y direction. So what I probably want is like a 3 here and a 0.5 here. Right? If the scale factor that caused us to get this angle was 6, right, I know that the magnitude I actually need to hit is 3. So I'll multiply, actually, so what I would need to have here is this value be 3. Right? And so in this case, I'm going to have to squeeze my x-axis a little bit in order to get the right eigenvalues. Everybody on board? And now, having done that, what do? Well, so if I rotate it by plus 45 degrees, now I need to rotate the rest of the way around. Right? Or if this was oriented in some goofy direction, if the problem I was trying to solve had looked like this, right, now there'd be that extra rotation. Okay. So we're going to talk about eigenvalues now. Any questions about singular value decomposition? So the goal of this was so that when you see singular value decomposition, you have some notion of how to look at the numbers again, right? The whole overall goal of this tutorial session is so that you stop seeing matrices as just opaque blobs of numbers. And hopefully now you can look at them and say, oh, I see. You know, these are columns. I know how to interpret these as columns. And you know, this as a rotation matrix. And this column here really corresponds to what happens to the x-axis, right? And the more structure you're able to sort of see in these matrices, the better you're going to be at solving these types of problems. Okay, so let's talk about eigenvalues. So eigenvalues and singular value decomposition are very closely related. In fact, if you think about the problem that we solved originally, which was regression, we picked the bottom row of V transpose, as the solution to our system. Right? Why is that? Well, because if we took that vector and put it here, it's going to get multiplied by the smallest possible value in our singular value matrix. Right? So in this case, this is, let's now, for simplicity, we'll just talk about symmetric matrices. So in symmetric matrices, the eigenvalue decomposition, U and V are actually the same matrix. Right? And this is actually the eigenvalue associated with A. So what does that mean? If I take one of the elements of U here, let's say I've got my U matrix. It's got a bunch of rows in it, U1, U2, U3, U4. And I pick one of them, I put it over here. What am I going to get out here?
Corresponding eigenvalue.
Say it again?
The corresponding eigenvalue.
That's what I'll get here, right? So as I multiply these guys out, I'm going to end up with basically an indicator vector, right, which is going to be still n by 1. And then when I multiply it here, I'm going to get the scale factor of that. And what am I going to get when I multiply, let's say if this was 6, 3, 2, 1. What's going to happen when I multiply 0, 0, 0, 0, 1 by this guy? I'm going to pick out the last column again. Right? So I'm not just getting the eigenvalue back out. I'm not just getting the eigenvector back out. I'm not just getting ui out. I'm getting 1 times ui back out. So what would happen if I picked u sub 2? Well, we're going to end up when we multiply this guy by this guy, we're going to end up with 0, 1, 0, 0, 0. Because this guy is going to correlate only with the second row of U transpose. Which means that when I multiply it by the S matrix, I'm going to end up with 0, 3, 0, 0. And when I multiply that by U, I'm going to end up with 3 U2. Everybody on board? So what is this saying? What is an eigenvalue? What is an eigenvector? An eigenvector is a vector that when you multiply A by one of its eigenvectors, you end up with lambda U back out. Right? You end up with a vector that's pointing in the same direction, and just the magnitude's been changed a little bit. right? And that's exactly what the SVD is telling us. It's telling us what the eigenvectors are and what their eigenvalues are. Does that make sense? So there's a great tool in MATLAB. Anybody remember? It's like the Eigenvalue Explorer tool. There's this little GUI where you can basically sit over here on the right side and you click around a unit circle. And as you drag it around, you're changing the vector on the right-hand side. And then as you're doing that, it's plotting A times that vector. And so what you'll find as you're doing this is, wow, I don't think I can do this. Here's the origin. Right, so this is my mouse click. I click here, and so this is u equals -1, 0. And so A times that vector might be here, right? Maybe it's a dead marker. So in this case, it got amplified a little bit and rotated a little bit. And then as I slide this guy around, of course, this guy's going to stay on the unit circle. So as I stay on this is going to intersect at places. Right? What happened right here? Well, it doesn't have to actually intersect, but they will be along the same chord. So let me do that again. So we were here. And so I might have something that goes like this. Right? At this instant in time, they're both at the same angle with respect to the origin. What does that mean?
That vector can be an eigenvector.
Yep, I found an eigenvector. Right? And how do I recover the eigenvalue?
Scale.
Right, take the length of this guy, divide it by the length of this guy. Right? And now, as I keep going around, this guy might start doing other weird things. It's my intention here to not have these meet all the time. But you guys get the idea, right? Maybe this guy lags behind now for a while, and then, bam. What did I just find? The other eigenvector. So in this one, the eigenvalue would be less than 1 because this guy is closer to the origin than this guy. Right, this is a pretty cool tool. I forget the name of it, but it's in MATLAB. It's kind of fun to play with. You provide your own A, and you can drag around and watch AX sort of do laps around you. And there's some interesting geometric intuition about how many times can these line up. Right? Well, in two-dimensional space, we know mathematically it can only be 2. If you play with this tool for a little bit, you'll get some geometric intuition. It can't be anything more than that, right? Because if it was more than 2, it'd have to be lapping or something like that, and it can't lap. It can't be 1, because that would mean you met at one point. There's no way to do that, right? I run out of space. Like this one had the opposite of being lapped, whatever that. So I can't explain that intuition very well to you, but go and try that, and you'll quickly develop some intuition why there have to be exactly 2 places. Now, those 2 places actually could be in the same place, because you could have a repeated eigenvector. No, you can't have a repeated eigenvector. You could have a repeated eigenvalue, so they can't be in the same place. Anyway, strike with the last thing I just said. I should stop making things up while I'm talking, standing in front of a classroom. That's the fun thing about intuition, right? It's right nearly 90% of the time. Okay, so let's cover a little bit more about eigenvectors, because they allow us to do something kind of cool. Let's suppose, so we understand exactly what the matrix A is going to do when we multiply A by an eigenvector. Right? We're going to get lambda I times that eigenvector back out. Well, what happens when I multiply some other vector by A? Well, you could actually take the SVD and multiply it out by u sub I. And what are you going to see? Well, I'm sorry, if this isn't u sub I, this is just some x. Right? This x will correlate with different fractions of these guys. Right? So let's suppose the eigenvalues are here, the eigenvectors are here and here. Right? And I have a third vector. All right? This is on video, right? That's great. How can I describe what's going to happen to this vector? Keeping in mind this is all linear. Multiplication is linear. So I could project this vector, the vector that I'm asking about, onto this vector and ask what a vector of that magnitude what's going to happen to that projection onto this vector. And I could do the same thing with this vector on this vector. Right? In this case, I know exactly what's going to happen to the projection of this vector on here and what's going to happen to the projection of this guy on here. Right? And because the eigenvectors form an orthonormal basis, the thing that happens to this is going to be the linear combination, the sum of what happens to the projection on here plus the projection on here. Okay, so can we write that out in equation speak? So a times x, here's x, right? This is the vector that's not an eigenvalue, is going to be the sum of what happens to, we're going to consider all of the eigenvectors in the system. A times ui, we want projection of this guy onto u sub I. So it's going to be the dot product of this guy times u sub I again. Right. Everybody see that? Right, here's my dot product. How much does the leg point in the same direction as this eigenvector? And then this is going to actually construct the corresponding vector again. So this is kind of cool. If I have an eigenvalue decomposition, I can think about how the system is going to evolve for any other vector by decomposing it into a sum of eigenvectors. And because the eigenvectors form an orthonormal basis, I can always do this. You give me a vector, I've got an orthonormal basis, I can build that vector that you're asking about as the sum of some other vectors. And so I put all of those vectors into A, and because those are eigenvectors, I'm going to understand where they're going. So does that make sense to everybody? Thumbs, please. Good. People are doing well despite the fact I'm sleepy and not being very coherent, which is fantastic. So this actually gives us kind of a cool method. Let's suppose that we want sort of the poor man's singular value decomposition, right? So there's actually a problem that's sort of let me do this in a different order than I had planned. So let's talk about a real-world application. Let's suppose I have some sort of random walk process. So I've got a graph maybe, right? And these are all places in the world. And then there are sort of edges that connect these guys, right? So what this might indicate, for example, is there's a path between this node and this node. And at every point in time, there's some probability that an agent here will follow one of the roads leading away from it. Right? So this would be a random walk on a graph. Every time step, we're moving to one of our neighbors. Right? And we can describe this as a transition matrix. We can describe the behavior of the agent on this graph with a probabilistic transition matrix. Right? If you are in this node, what's the probability that you transition to any other node in that graph? So let's number these real quick and just write a transition matrix. And the way that we're going to do this is, let's suppose that we start off in some state, and we're going to characterize that state as a probability density. So let's suppose we're in state x. X is a 5×1 vector, which gives me the probability that at time equals 0, I'm in any one of these 5 states. Right, so what do we know about the sum over all the elements in x? Must be 1, right? The agent's got to be somewhere. Right? Note that this is different than the length of x being 1. Right? In this case, it's actually the sum of the elements is 1. Okay, so x is 5 by 1. And what do I want at time equals 1? Right, here's x equals 0. Here's x equals 1. This needs to also be 5 by 1, which means what do I need this matrix to be? 5 by 5. That actually makes good sense, right? That gives me the maximum possible flexibility in describing if the state agent was in state I can list a probability for every other state where it could go. The fact that this graph has a lot of missing edges in it is just going to mean that there's a lot of zeros in this graph. Okay, so here's a question for you. We know if I'm in state 1, let's suppose that means there's a 50% probability that I go to state 5 and a 50% probability that I go to state 2. In this case, 0% probability that we stay still. So we know that somewhere in here is going to be the vector 0, 0.5, 0, 0, 0.5. Right? Here's the probability that I end up in state 2. Here's the probability that I end up in state 5. Is this a row or a column in this matrix? Anyone else? So how can we test this? Well, let's use the same trick. This is really a projection problem, right? We're projecting from one space into a next space. In this case, it's the same coordinate system. It's just allowing for the passage of time. So what's a nice vector that I could put on the right side that I can understand something about the behavior on the output? Yeah, so what happens if we put 1, 0, 0, 0, 0 over here? Right, forgetting what's in here, what does this guy got to be? It's got to be this vector, right? 0, 0.5, 0, 0, 0.5. And given this, does this need to be a row or a column, and where does it go? It's a column, right? Because this guy's basically a selector. It's pulling out the first column, right? The 1 is always lining up on the leftmost element. So in fact, this here is the probability transitions. Given that I'm in state 1, where do I go next? And so what do I know about the values in this column? They had better add up to 1. What about the guys here in the rows? Should those add up to 1 too? The rows. Do the rows need to add up to 1? No. No, in fact, I could have a problem where state 1 was an absorbing state. No matter where you went, you always went to state 1 next. Right? What would that look like? What would that transition matrix look like? If state 1 was one of these states that just sucked everybody in like a black hole. Right, I'd end up with 1, 1, 1, 1, 1, and zeros everywhere else. And it's basically saying, no matter what state I was in, my next state's going to be 1. That's kind of cool. Right, so the columns need to add up to 1, the rows do not. And again, the best way to keep this straight is not to try to memorize it, but to try a simple example and try to figure out what's going to happen to the columns. Okay, great. So let's suppose we go through and we fill out this whole matrix. Let's call it A. I'm being creative today. And at time 0, I'm at state x0. What is my probability distribution at time 1? AX, 0. What is this is x1. What is my probability distribution after 2 random transitions? Yeah, you guys are already seeing this, right? This is x sub t is AT x naught. Well, that's interesting, isn't it? So what does this mean? It has some interesting implications. What does it mean? As I start plugging in bigger and bigger values of t, what do we expect to happen? We think it's going to start sloshing around ever more violently and randomly, or is it going to converge to something? Not necessarily. So a simple counterexample to that would be if I had this all-absorbing black hole state, then a to the infinite power times x naught is going to be 1, 0, 0, 0, 0. Right? It's not necessarily going to blur out the probabilities uniformly. Another example, intuitively, let's suppose I had this graph. Did I miss any edges there? Yeah, let's add a few more in here. Right. So imagine this as a sort of hypothetical graph. Here is a really richly connected area. Right? This is an area that you're not very likely to stay in for very long. Right? Here, once you get in here, there's all kinds of transitions. You might end up staying around here a long time. Right? So what would you expect the steady state distribution to look like? Yeah, right. High probability that you're going to end up here, low probability that you're going to be here. Right? And you can see that just from sort of the density. You're more likely to stick around this area because there's more transitions that basically bring you right back to that cluster. Okay, so how can we analyze the performance of this system? So there's something about the properties of A that are going to determine where this is. In fact, does it matter where I start, where my steady state distribution is going to be?
It depends upon the graph.
Right, so if the graph was really degenerate, if I had this, it would depend. Right, because if I started here, then guess where I'm going to be? But assuming the graph is fully connected, does it really matter where I start? Does where I start really affect where I'm going to be at time equals infinity? No. No. So that says something interesting, that I should be able to analyze the system without even knowing x. Now, who's got a guess? Who's got a guess what properties of A are going to tell me about the steady state distribution? Eigenvalues. The eigenvalues, right. So any guess what the steady state distribution is going to be? If you had to...
Probably the eigenvector which has the maximum eigenvalue.
That's exactly right. Right? So the eigenvector with the maximum eigenvalue is the steady state probability distribution for a random walk on that graph. So if you've got a graph with a transition probability matrix like this, the eigenvector with the largest corresponding eigenvalue gives you your steady state probabilities. In other words, A to the infinite power times any vector at all, caveat, asterisk, legalese, that is going to be equal to the steady state distribution. Right? And what's happening is that the eigenvalue with the largest magnitude dominates. Right? As I take A and I multiply it by A again, let's suppose that I've got, here we go. I've got an A with an eigenvector this direction and an eigenvector over here. And this one's got an eigenvalue of 50, and this one has a magnitude of 1. Okay? Let's suppose that I start off pointing sort of over here. So this is x. What is AX? Right. So we can project it both onto this eigenvector and onto this eigenvector. It's going to have a large dot product with this eigenvector, but it's only being multiplied by a very small eigenvalue. Right? The projection onto this eigenvector is small, but it's got this 100x eigenvalue bonus. So I started here. After one time step, I'm probably already here. Right? It's pulling me in the direction of the dominant eigenvalue. So if I take any random vector at all and keep multiplying A on the left of it, what's going to happen? I'm going to end up pointing in the direction of the dominant eigenvector. With one caveat. How can this go wrong? Say it again? Zero vector, yes. So let's not pick the zero vector. One more thing that can go wrong. Yeah. What would happen if I actually picked a starting vector that was perpendicular to my happy vector? Well, the projection is 0 at time step 1, and the projection is 0 at time step 2, and on and on and on we go, right? But what's the probability, if I'm randomly sampling numbers from a random number generator, that I'm going to sample an n-dimensional vector that is perpendicular to some specific other vector in space? It's close enough to 0 that we don't really need to worry about it, right? If you had 64-bit float, goodness. Even if you were talking about a two-dimensional space, you'd have to get unlucky for about 128 bits. Right? So 1 and 2 to the 128 in two-dimensional space. That's probably optimistic because there's probably numerical precision issues that would mean that there are a greater number of randomly generated double values that would end up truncating badly. But in any event, we're talking about one in a very huge number of events. Yes?
But this was assuming that the eigenvectors are, first of all, orthonormal, as in perpendicular to each other. And also, suppose I have two eigenvalues, but both are greater than 1. Then as t tends to infinity, then both should contribute, right?
Yes. So two good questions. So the first one is that my first argument, so the eigenvalues are not necessarily perpendicular to each other. They're only perpendicular to each other in the event that for certain classes of matrices. So symmetric matrices are one of them. So ATA is a happy matrix because the eigenvectors will always be perpendicular. That's not necessarily always the case. In fact, with a transition matrix like this, they're not likely to be perpendicular because this is not a symmetric matrix. Right? We know that because this column has to add up to 1 and this one doesn't. Right? So it clearly does not have to be a symmetric matrix. In that event, the same thing is still true. If the eigenvalue I'm hunting for, I randomly pick one that's perpendicular, I'm still in trouble. But it's not necessarily the case that the unlucky ones correspond to other eigenvectors. Right? It's still the case that I can get unlucky. But actually, if they weren't perpendicular, then you should pick up a component from, like if they were like this. No, it's still going to be a problem. The second question had to do with, let's suppose that my x is here, and the eigenvalue for this guy is 50, and the eigenvalue for this one is 50,000. Right? Same sort of behavior is generally going to happen as my system evolves and I keep multiplying by a. The direction of my vector is going to keep going closer and closer here. But something else bad is happening from a numerical precision perspective. Right? The magnitude, the length of that vector is growing by at least 50x at every step. Right? So very quickly you're going to saturate your double precision numbers and everything's going to explode. So what do you do? Right. The only salient thing about the eigenvector is its direction. Right? So at every step you can always just throw away the magnitude and keep doing the multiplication. So you normalize at every step, and then you avoid the numerical precision problem. Yes? Right. So then you're going to wander. You're going to wander in the direction of one of them. Then you'll keep going in the direction you were in, right? Because you're going to keep projecting. So the question is, what if you have two eigenvectors that are tied for the largest eigenvalue? And so in one case, suppose that these are all fungible, right? And so suppose your S, right, it's all in a subspace. Any starting vector that I have that starts off anywhere in that subspace is just going to keep getting amplified in its current direction. That generally doesn't happen. All right, so let me ask question.
The elements of the elements of the eigenvector, especially the largest eigenvalue, the steady state probability of the states.
Yes. Yep, exactly right. So let me ask another question. Let's suppose I had actually 100 nodes over here, and they're all fully connected. Then I've got a little chain over here and I've got another little cluster of 20 nodes, and they're densely connected. What do you think happens? Yeah.
The probability of those densely connected parts will be higher than the
You're close, but it's not quite right.
The initial state will affect what the final state will be. If the initial state starts in one cluster, the probability of ending up in the second cluster will be low.
Not as time goes to infinity. It's certainly the case for small values of t that if I start closer to here, then after some finite number of steps, I'm probably more likely to end up here than over here. But let's still consider the steady state case.
you're still very likely to end up in the higher connected portion, but way less likely to end up in the lower connected portion.
That's right. Right, and so this is going to be manifest in the eigenvalue, in the singular value decomposition of A in a very specific way. Right, so intuitively, we understand that there's actually still something going on here, right? If you got stuck down here, you're likely to stay down here. But there's something mutually exclusive about getting stuck down here with getting stuck up here, right? You can't be stuck simultaneously in both of these, right? So there's sort of an or, right? There are two explanations of what might happen. You might end up here, and you might end up down here. Yes?
Here's just a related question. Can you think of this as if that last node before you added on all of the bottom, before you added all that on, that had some probability in steady state, does that probability essentially get split among now that large graph in the bottom?
No, something much cooler happens. Any guesses? Yeah.
I think when you have two nodes, when you have a probability of node A to B, it's not the same as probability of going from B to A.
It does not have to be.
So it could be unidirectional, the link in a way that, one of the elements would have a probability of going one direction or something.
It absolutely could be. In this case, let's just assume that my edges are nice and bidirectional. Now, I'm not trying to be evil in this example. But you're right. You could have asymmetric transition probabilities. Another example of that would be the black hole, where everybody always transitions to state 1, but nobody ever transitions out of state 1. So here's what's going to happen. And when I first saw this, I thought this was the coolest thing ever. Your dominant eigenvalue is still going to be high probability mass here, low probability mass here. What do you think happens to the second eigenvalue? The second eigenvector. The second eigenvector gives you this solution. Right? So your eigenvectors are actually giving you different sort of parallel universe outcomes. Right? Because they're disjoint, right? It's saying that either you end up over here or you end up over here. And so in the world that you end up over here, here's the probability distribution. And the eigenvalue tells you how often that outcome actually occurs. In the second alternative universe, you might end up down here, and you're going to end up with a different steady state probability distribution, but with a smaller eigenvalue. Right? So still, your best t equals infinity solution is up here, but what you find is that the next best high order correction to your probability distribution says that, well, actually, you're down here. Yes?
So are we saying the other one had like a little bit more nodes or something?
Yeah, let's say this one had 1,000 nodes and this one had 500 nodes.
That equal nodes type would be like just a labeling problem because I could start to count down here.
So there are numerical issues here that make the story I'm telling not exactly right, but qualitatively, if you had 1,000 nodes here and 1,000 nodes here, if you set up the problem so that numerical issues didn't screw up your answer, you would end up with a duplicate eigenvalues, one with a lump up here and the other one with a lump down here. Yes?
So we use this process for clustering graphs then?
Absolutely. Right, so you can do clustering in graphs by looking at the distribution of the eigenvectors. Every eigenvector is telling you something about a clump of nodes that have high transition probability. Right, so if you were Google and you went out and so how many of you know how PageRank works? Yeah, so PageRank is a random walk algorithm. Right, so basically, every node in here is a web page. And the links represent links. hyperlinks. And so basically, in the original PageRank algorithm, of course, Google has twiddled with this endlessly since then. They won't tell us what they do anymore. But in the classic PageRank algorithm, a page is scored high in your search results if it is well connected, or which is to say that there are lots of links going in and out of it, which is to say that it's part of a densely connected neighborhood like this. So the way the PageRank algorithm works is that they go through, they harvest a bunch of web pages, they build this transition probability matrix, and you can view the score associated with an individual web page as being the steady state probability of ending up there if you started on a random web page in the universe and started randomly following links. That's kind of cool, right? So the more people who link to you, the more likely your page is to be in that steady state distribution. Have a higher probability in that steady state distribution. It's awesome. Okay. This also suggests an interesting way of computing the dominant eigenvector for a matrix. If you don't want to compute the full SVD, what could you do? Say it again? Yeah, pick a random vector, just keep multiplying a times that random vector. Multiply by a over and over and over again, normalizing after every step so that you avoid running into numerical precision issues. And with vanishingly, with extremely high probability, it'll converge. Okay, what if you wanted, let's suppose that A is full rank, the A matrix is full rank, and you want the minimum the eigenvector corresponding to the minimum eigenvalue. What can you do? Say it again? Yeah, do the same thing on A inverse. Right? Because what is A inverse going to do? It's going to switch the magnitude of all the eigenvalues. So they use the power method on A inverse, and you're going to end up with the smallest eigenvector of A. Yes?
What is the converge value?
What is the
Converge value.
What is the convergence? How fast does it converge?
No, what is the result? Like, what does that number tell you?
So you would actually, if you do the power method, right? You're starting here. You keep multiplying. The vector that you end up with is the eigenvector, the dominant eigenvector of that matrix. All right. So here's another fun thing. Suppose you've got a system and you happen to know that one of the eigenvectors, that the minimum eigenvector is 2, and you want to no, I'm sorry, I need to ask this question in a different order. How quickly does this process converge? Let's suppose that I'm in 2 dimensions and my eigenvectors are lambda 1 and lambda 2. How rapidly does my vector shift over? Say it again? Yeah, actually the ratio ends up mattering more than the difference, but you got the right idea. Right? The bigger the ratio, the faster I'm going to switch over. Right? If this is the largest eigenvalue in the matrix, and this is the minimum one, the ratio lambda 1 over lambda 2, I'm sorry, in general, this ratio is called the condition number of the matrix. What is the condition number for a rank deficient matrix? Infinity. Right? So for numerical stability issues, we don't like matrices with large condition numbers. But a matrix with a large condition number is great for the power method. Right? It's going to go really fast. I started asking another question. I was going to talk about the power shift method, but we're going to skip that because it's 9 o'clock. Okay, so there are 2 other things I want to talk very briefly about. You guys are doing great. One of the topics I promised to cover, I've got to cover this one. So you've used the power method to extract the dominant eigensystem, the dominant eigenvector and eigenvalue from a matrix. What if you wanted to get the next largest eigenvector? What would you do? Yeah. Say it again? Yeah, you're on the right track. That's interesting. Yeah, that should work. So there's a slightly scary thing that can happen with that particular thing. I think that would work well with an infinite precision machine. One problem that might occur is that the matrix itself might still have this really huge eigenvalue in it, and any rounding errors that occur might start slowly increasing the dot product of your random vector, which started off perpendicular, but just due to rounding, it might end up with a non-zero dot product, and then before you know it, boom, you're back where you started. Yeah?
Can you reduce the dimension of the matrix?
Yes, you can. Right, so you can extract all of the dominant eigenvalue-y goodness from that matrix. Right, so if A is symmetric, and let's suppose I do this. Oops. Let me actually write this a slightly different way. The A matrix, if you think about the singular value decomposition, remember that S is block diagonal. And that gives us sort of an interesting way of writing the matrix A. So A is the sum over I of U, I, vector, yes, S, I, V, I transpose, something like that. Right, so this block diagonal, this diagonal matrix S is basically decoupling all of the terms that contribute to it. Right, so I could expand this product. A is equal to this vector plus this vector plus this vector plus this vector, each one scaled by the corresponding diagonal element of S. And none of the cross terms matter because S is 0 everywhere else. So I can write A as the sum over all those individual contributions. Now we're home free, right? If I've extracted UI and VI, and if A is symmetric, they're the same thing, then I can just subtract off this amount. I subtract off U, S, V transpose. So A minus. So I compute a new A that lacks all of the dominant eigenvalue-y goodness of the previous A. This is going to avoid the problem that you suggested that your method has, because now we've just taken away all of that high eigenvalue component, and now we restart with another random value. Awesome, right? It's cool. Okay, so one thing that, how many of you have heard of principal component analysis? Right, you already know what principal component analysis is. It's talking about a set of points by looking at the dominant eigenvector. Right, it's actually what we started with. Right, when we can fit a line through a set of points, we're fitting a line in the direction that is the principal component of all those points. Right, so we started the day with principal component analysis, and we just didn't call it that. Right, easiest thing you've learned all day. And we should really stop here. Let's do a question.
In general PCA, the biggest eigenvalue indicate in which dimension the data value is the most.
That's right. So imagine in fitting points, right, so here's a bunch of points that I went out and I collected. What's the best line fit? Well, it's something like this. Well, and that best line fit is also in agreement with the direction of maximum variation. It also turns out to be the principal axis of the covariance matrix. Right, that is also the principal component. So the same notion of looking at a set of points, constructing that the outer product associated with those points. Because remember, we ended up with this sum of pi transpose pi, p, like that. Right? This matrix here gives you the covariance matrix for those points. And the dominant eigenvalue of that is the best line fit in the sort of perpendicular sense. It's also the principal component. It's also the principal axis of the dominant of the covariance ellipse. So it's all the same thing. Other questions? Yes. Right. So in this case, I'm using little u's to represent the individual columns and rows of big U and big V. And so what I mean here is that if I had the full SVD decomposition of A, right, I could actually recompute A by doing this. Now, if I've done the power method, the only ones I actually know are U1, S1, and V1. Right, because my power method will give me, will pull off the dominant eigenvector and eigenvalue at every step. And I don't actually need to know the others. I'm just going to take my old A and subtract off the component in the dominant direction. Great. All right, thanks everybody. I hope this was helpful to you. Good luck. We'll see you in 568, or we'll be doing this probably again next year. So if you have friends who wish they were here, or if you want to subject your friends to it, tell them to come next year. Thanks.